Hello and welcome back. This is the third lecture on special relativity. In the last class, we saw that Einstein had come up with a few simple postulates on which to base his new relativity principle. Two of these key postulates were: one, the principle that all inertial observers experience the same laws of physics. And the second, and this is where he made a break with Galilean relativity, was to assume the principle that the speed of light c is a constant for all inertial observers. That is, every single inertial observer will perceive the speed of light c to be exactly the same. We saw that these simple postulates had very dramatic implications. We saw the first of these implications in the last class, and that was that simultaneity is relative. If you take a particular inertial observer who sees two events occurring simultaneously but at different spatial locations, these events will not appear to be simultaneous to an observer who is moving relative to that first observer. Today we will see that the relativity of simultaneity in turn implies relativity of lengths and times. That is, the length as measured by one inertial observer will not be the same as the length measured by a second inertial observer moving with respect to that first one. Secondly, clocks which are moving with respect to a particular inertial observer will appear to tick at a different rate than the clocks held by the ground observer. These two facts, the fact that lengths can be relative and times can be relative, are dramatically different from what we expect in Galilean relativity and Newtonian physics. We will then go on to derive the transformations of special relativity, or the dictionary of special relativity, to translate from one inertial observer to another. We will see that this dictionary follows very simply from Einstein's postulates of the special theory of relativity. So here's the plan for today. We'll start by talking about the idea of synchronization of clocks. Then we will discuss again the relativity of simultaneity in light of that discussion of synchronization. And we'll see how the relativity of lengths and times follow from the relativity of simultaneity. Then we'll define a couple of terms that will be useful since we're departing from our conventions of Galilean relativity. And finally, we will derive the special relativity transformations. So the first thing that I want to do is to show you that not only is the speed of light c a constant for all inertial observers, but the postulates of special relativity would also imply that the speed of light c is a maximum speed for any inertial observer relative to another. Let's see how this works. So let's imagine that you have an observer O, and observer O sees a light beam moving to the right at speed c. And now let's imagine that you have another observer, O prime, who is moving to the right with the speed v. Now, by the postulates of special relativity, observer O prime should perceive the speed of this light beam as being c relative to themselves. But also, the observer O prime should perceive the light beam as moving to the right for as long as their speed v, as seen by observer O, is much less than c. However, once observers O prime's velocity or speed becomes larger than c, they would, as seen by observer O, appear to overtake this light beam. So it necessarily means that at some point observer O prime would by the postulate of special relativity, they must perceive the speed of light to be c always, but they would now perceive the light beam to be moving to the left rather than to the right. So if the speed of observer O prime could be greater than c, what you would get is something like this. So here I'm plotting on the x-axis the speed of observer O prime as measured by observer O. And what we're going to do is we're going to plot the velocity of light as seen by O prime. So for speeds less than the speed of light, you should see a positive speed, that is a speed, if I take my reference axis to be positive in this direction, you would see a speed which is plus c for this light beam moving to the right. But once you overtake that light beam, supposing your speed is greater than c, then you would necessarily see that this object the light beam has a velocity to the left, and by the postulate of special relativity, the magnitude must still be c. So there would be a discontinuous change in the velocity of the light beam as seen by observer O prime. This kind of discontinuous change is obviously unphysical, just from the fact that you don't expect any change, a dramatic change in the direction of the light beam, just as you increase your speed from slightly below c to slightly above c. So therefore, it must be true that the speed of light c is actually a limit of the speeds of observer O prime relative to observer O. So let's write that down. The speed of light c is a speed limit for any inertial observer O or O prime relative to another observer O. So now let's see what the implication for this maximum speed limit is when you try to synchronize clocks. So let's go back to thinking about the people waiting on a railway platform. So let's imagine that you have an observer O, and he has a few friends with him waiting on a railway station platform, and these friends are separated by some distance L from each other. Okay, and this distance L is as measured by meter sticks, which are at rest with respect to O and these friends on the platform. So now let's suppose O has a clock, F1 has a clock, F2 has a clock, F3 has a clock. And they want to synchronize their clocks so that they can measure when a particular observer on a train passes them. Okay. Now, since there is a limit to the speed of any signal or any observer as measured by these friends on the platform, there is a maximum speed limit with which these observers or these friends on the platform can communicate with each other, and that speed limit is c. The best or the fastest way they can communicate with each other is to send light signals from one to another. So how would observer O and his friend F1, say, synchronize their clocks with each other? So what observer O would do would be to start off their clock at time t is equal to 0. And they would instantaneously send a light beam to their friend F1. So at the same instant that they start their clock, they send a light beam to friend F1. Now they know that their friend is a distance L away, and therefore the time it would take for this signal to reach their friend would be a time L by c later that this signal reaches their friend F1. Now F1 also knows that O has agreed to start their clock at the time at which they send their light beam, and they know that it will take a time L by C for this light beam to reach them. So what F1 does is that the instant that F1 receives the signal, they will set their clock to a time of L by C. Okay, so now even though they cannot simultaneously see each other's clocks because the speed of light is a barrier which prevents them from instantaneously perceiving what is happening on each other's clocks, they know that now their clocks are synchronized with each other by this procedure. So by a similar procedure, friend F1 and F2 can synchronize their clocks, and friend F3 and F2 can synchronize their clocks, and so on. So now you can have a whole bunch of people sitting on the platform who all know the distance between themselves and who have a bunch of synchronized clocks. Okay, so this procedure for synchronization is called synchronization with light signals. There is nothing particularly special about this procedure for synchronization. However, you have to think carefully about how you would achieve synchronization given the fact that you cannot instantaneously communicate between these different friends. So now that we understand this procedure of synchronization of clocks, let's go back and look at the relativity of simultaneity once again.